In this last video, we're going to be looking at compounds that have two rings, and we're going to be looking at heterocyclic compounds. Those are compounds where one of the carbons has been replaced by another atom. Okay, so when we have two rings, there's a special nomenclature system that we use. We first have to identify the carbons that we designate as the bridgehead. Then we're going to count the number of carbons that are spanning the bridgehead. So let's just look at this very first one right here. These carbons here are the ones that we would identify as the bridgehead. Okay, we're going to count the number of carbons that are spanning the bridgeheads. There's two carbons there. There's two carbons there. And there's one carbon there. In a bicyclic compound, we should end up with 3 spans. Okay, now after doing this, we're going to name the compound. It's going to be named bicyclo, in brackets, X period, Y period, Z period, where these are the numbers of carbons in our spans, and close bracket, and then we're going to name it as a derivative of the total number of carbons in the bicyclic ring system. Okay, so since we're not counting the bridgehead carbons in the span length, what we end up with is where the numbers that you add together should come up to be 2 less than the total number of carbons in the bicyclic ring system. So in a bicyclodecane, X, Y, and Z should add up to 8. We're going to place them in descending order. The largest span is first, followed by Y and Z. Okay, so let's look at a couple of examples of bicyclic compounds. Alright, so here, this is bicyclo 2,2,1 heptane, 2 carbon bridge, 2 carbon bridge, 1 carbon bridge between the 2 bridgehead carbons. We're numbering them in descending order, bicyclo 2,2,1 heptane. In this compound right here, okay, here's our bridgeheads. If we count our spans, there's a 3 carbon span, a 2 carbon span, and a 1 carbon span. In this total bicyclic system, there are 8 carbons, and thus the name bicyclo 3,2,1 octane. Okay, here's one it's a little different in that one of the spans really doesn't have any carbons in it. Okay, so here we have 3 carbon span, an identical one here. And notice that the bridgehead carbons are directly attached to each other. This means that there's 0 carbons in the span here. Okay, so this is a bicyclo 3,3,0 octane. Okay, this one we're going to come back to in the next slide because this is an important molecule. This is bicyclo 4,4,0 decane. Again, you can sort of see how it would have that name. It's just basically the previously looked at compound with 1 extra carbon in each ring. This is also has the name decahydronaphthalene, which has been shortened to decalin, and this is the common name for this system. Okay, and this is a compound here where there's all the spans are identical to each other, and this is bicyclo 2,2,2 octane. If we look at these two compounds here, we'd have to say that these two compounds are conformationally very rigid. Okay, they can't really move their atoms very much without causing extreme degrees of strain. They also are frozen, or even though they're rigid, they have a lot of torsional strain. Okay, so in this compound, bicyclo-2,2,1-heptane or norbornane, we see that two of the carbons are actually perfectly eclipsed, and they can't get out of that. The ring is quite rigid. In bicyclo-2,2,1-octane, we have actually 3 pairs of eclipsed carbons. The other ring systems here have a little bit more flexibility, but not as much as you might think. All right, so in bicyclo-3,2,1-octane, you can sort of see embedded in here a chair cyclohexane, right? So let's imagine that this chair cyclohexane undergoes a classic ring flip. Okay, so as axial carbons here, they're fairly close, and they form a nice strong bond. But when these carbons are equatorial here, these carbons here are so far apart that they can't make a bond anymore. And in fact, the bond that they do make is kind of crammed into this area here. It has to actually go through the other parts of the chair cyclohexane ring. So it can't really do that. So this inability to do the ring flip means that this compound here is what we call conformationally locked. Okay? It's a chair, and it has to be that chair. It can't be the ring flip chair. Okay, decalins present another situation. We have 2 types of decalin ring systems. We have cis, where the 2 hydrogens are cis, and we have trans. And these are very different in their ring flip dynamics. Okay, cis-decalin, if we look at how things orient relative to this ring right here, we see that one of the CH2 groups in the other ring is axial, and one of the CH2 groups is equatorial. Okay, we can go ahead and ring flip that, and that just changes that around. Okay, so in cis-decalins we have relatively rapid ring flips, just like any other cyclohexane derivatives. However, with transdecalin, we can't have ring flips. Okay? Alright, so in transdecalin, the ring fusion is perfectly equatorial, right? If we look at this ring and how this other ring orients itself relative to that ring, both of those CH2 groups immediately attached to that ring are equatorial. If you try and ring flip this compound, what happens is that you take this CH2 group, now axial, and this CH2 group, now axial. These are so far apart that you can't span them with a 2-carbon link. Okay, so transdecalin, we say, is also a conformationally locked system. Another conformationally locked system is T-butyl cyclohexane. And the reason for that is kind of simple. T-butyl is just very large. And it's so large, in fact, that it doesn't want to do this process here. The 1,3 diaxial interactions are too severe. So T-butyl cyclohexane derivatives typically anchor themselves in a conformation where T-butyl is equatorial. Okay, we will revisit these conformationally locked systems because we need the locking allows us to view stereochemical requirements in other reactions, and we will revisit these systems in chapter 5 when we talk about something called the elimination reactions. Okay. Here's a problem. Again, you should pause the video and do it, and then restart it after you're done to just check your answers. Add to the drawing of transdecalan below so as to represent each species. Okay, so I'm going to just call these carbons 1, 2, 3, and 4. And this is the orientation they have in this partially finished drawing here. Okay. And the most important detail I can give you is that this is a transdecalan, and thus it's conformationally locked. So we do not have to consider any ring flips here. This is the only chair I can have for a transdecalan. All right, so the task you're now faced with is axial up or down at specific carbons. Well, at carbon 1, of course, axial is down, and at carbon 2, axial is up. And that's going to be our guiding principle for finishing this problem. Okay? So if it's up at carbon 1, it would have to be equatorial. If it's up at carbon 2, it would have to be axial. Okay? All right, so let's look at the answers. All right, so here, remember, axial is down at carbon 1. So that means equatorial must be up, so OH is equatorial. Okay, and in the other one, we're just moving it over to carbon 2. It's still up. This means that it has to be axial. Right, this compound here means that this one has to be equatorial, and this CH2 has to be equatorial, because again, it's up. CH2 is up here. It's where hydrogen is not, therefore it's up. And it's down at carbon 2. Therefore, it's equatorial also, and this we have the perfect all-chair ring fusion over 3 different rings. Okay, this one is going to be the same here, but it's going to be opposite here. It's going to be axial, and this CH2 is going to be equatorial, and this is the ring system that we would have here. So this is equatorial relative to the original decalan ring system, and this CH2 group is axial. Okay. Here's another question. Which of these two bicyclic compounds is more stable, and why? Again, pause the video and just think about it. I think it's pretty easy to see that there's some rather severe steric things happening in this one, right? Okay, so our 1,3 diaxial interactions here are with CH2 groups. Here, our 1,3 diaxial interactions involving the methyl group are only with hydrogens. And this is a lot more severe. Okay, so I think in this next slide I actually have it answered. Yes, so we have very severe 1,3-diaxial interactions in the compound on the left and less severe interactions on the right. This is also an example, remember, of a conformationally locked compound. We can't do a ring flip and get out of the fact that the CH2 bridge here is fused in an axial fashion. Okay, so the one on the right is more stable because the 1,3-diaxial interactions with hydrogens are not as severe as the 1,3-diaxial interactions with CH2 groups. Okay, let's look at heterocycles. I'm not sure, I don't really want you to memorize the names for all these, but when we think about the conformational analysis, the rules don't change just because we turned a CH2 group into an oxygen or into an NH. Okay, these are just some representative heterocycles. There are a lot more than these. Most of the heterocycles known contain one or more nitrogens, oxygens, or sulfurs in the ring. Those are the most common types of heterocyclic compounds. Okay, the same rules for conformational preferences exist in heterocyclic rings as in all carbon rings. Okay, so the six-membered rings here, the tetrahydropyran, would also exist as a chair. Okay, one of the pairs of CH bonds has been replaced by a lone pair, but it still basically prefers the chair conformation. Okay, and piperidine, we have the orientation, the equilibrium that you see here, where this compound on the right is favored at equilibrium. And what you see is that we have the lone pair is axial and the CH bond is equatorial. Okay, so the lone pair is the only thing that's smaller than a CH bond and loses out to a hydrogen in the axial equatorial preferences. Okay? Alright, so let's look at some other examples. So axial versus equatorial is very important in nutrition. Okay, the only difference between fiber or cellulose is the fact that we have an equatorial CO bond in fiber versus starch, which is caloric and digestible, and this has an equatorial CO bond. Okay, so axial versus equatorial decides on whether, like, your cereal is mostly fiber or mostly digestible carbohydrates. Okay? Alright, so here's again a situation where axial, equatorial makes a big difference, right? You can't live on, or you can't supply your body with energy through equatorial CO fused glucose units. Okay, this is okay, but you can supply them, your body, with nutrients through axially fused glucose units. Okay, knowing molecular shape is very important to drug design. This is oseltamivir, or the common general purpose anti-flu medication known as Tamiflu. And this has the distinction of being the first successful drug designed on a computer. And what happened was someone looked at a protein and said it has places in the protein that would hydrogen bond right at this location, and at this location. And somebody came up with this as would be the perfect compound to make and to inactivate the flu virus. This protein segment was common to a lot of different strains of the virus, so it's one of the few general treatments for the flu. Okay, and of course you'd have to know the precise conformation of this compound to figure out that it could function in this way. Here is actually the three-dimensional drawing of that compound. And so knowing the molecular shape is a very important tool in the design of novel pharmaceuticals, particularly when you're looking at compounds that are completely unnatural. This is a very different way of designing pharmaceuticals from the classic way. The classic way was to isolate things from nature and see that they're basically already doing what you want them to do. That's how antibiotics were isolated. They saw that bacteria were killing other bacteria and they wanted to find the compound that was causing that. Where here is a completely unnatural compound that was designed knowing the shape of a key protein in the virus. Okay, so this will end out the conformational analysis section of the class, or chapter 3.